In previous topics, we have introduced a general form of an optimization problem, which has the object function, constraints, and the variables. Such kind of an optimization problem is usually called a constraint optimization problem. In some situations, the optimization problem has the object function only. There are no constraints. That means all variables can vary from negative infinity to positive infinity. Such kind of an optimization problem is called an unconstrained optimization problem. We first focus on unconstrained optimization problems. Why we need to discuss unconstrained optimization problems? There are two reasons. The first reason is that unconstrained optimization problems inherently exist in some real situations. The second reason is that when we solve constraint optimization problems, we usually convert constraint optimization problems into unconstrained optimization problems. Then, the methods that are used to find the optimal solution for unconstrained optimization problems can be applied. In general, there are two methods that can be used to find the optimal solution of an unconstrained optimization problem. They are analytical methods and numerical methods. In the analytical methods, we use the necessary conditions to identify the stationary points. That is, we let the first derivative or first partial derivatives to be equal to 0. Then we use the sufficient conditions to classify the stationary points into minimum, maximum, or saddle point. When we let the first derivative or the first partial derivatives to be equal to 0, we may generate a nonlinear equation if the object function has one variable, or a set of nonlinear equations if the object function has multi-variables. Then we need to find the real roots of a nonlinear equation in one variable, or we need to solve a set of nonlinear equations in n variables. The analytical methods are usually difficult to apply for nonlinear object functions with more than one variables. This is because we need to solve a set of nonlinear equations in n variables. Solving a set of nonlinear equations in n variables can be just as difficult as solving the original optimization problem. Numerical methods can be used to solve the optimization problems directly. They are often more effective than the analytical methods, especially for nonlinear object functions with more than one variables. The numerical methods often benefit from the high-speed computers. In topic 12, we have already demonstrated how to use the analytical methods to find the optimal solution for an unconstrained optimization problem. In this topic and the following several topics, we will introduce numerical methods that can be used to search for optimal solutions for unconstrained optimization problems. In this topic, we will focus on one-dimensional unconstrained optimization problems. That means the object function has only one variable. Although there are many methods that have been developed for one-dimensional unconstrained optimization problems, they are generally classified into two categories, including function value-based methods and derivative-based methods. In the function value-based methods, we search for an optimal by evaluating function values at a sequence of trial points, such as x1, x2, and xn. The function value-based methods do not use derivatives. These methods are often inefficient. One popular function value-based method is the bracketing method. In the derivative-based methods, we use derivatives at each iteration and determine potential optimum by the necessary conditions. There are two popular derivative-based methods, including Newton's method and the secant method. Based on this, you can differentiate the function value-based methods and the derivative-based methods based on whether the derivatives are used or not. If a method uses derivatives, then this method is a derivative-based method. Otherwise, this method is a function value-based method. Next, we will introduce the bracketing method, Newton's method, and the secant method. Before we introduce the bracketing method, we first talk about a general procedure of function value-based methods for a minimization problem. In this procedure, we start from an initial value x0. This initial value is provided by us. Then we evaluate the function value at x0. After that, we will use some strategy to find another trial point x1 for the next iteration based on x0. For instance, we can simply let x1 equal to x0 plus 0.1. Based on this, we can find another trial point x1 based on x0. Then we also need to evaluate the function value at the next trial point x1. We compare the function values at x0 and x1. If the function value at x1 is less than the function value at x0, that means we find a better solution. Then we continue. Otherwise, if the function value at x1 is greater than the function value at x0, then we should revise the strategy and try to find another trial point x2 to make sure the function value at x2 is less than the function value at x0. We do iterations. At each iteration, we need to make sure the function value at the new trial point should less than the function value at the current trial point until the absolute difference of the function values at two successive trial points satisfies a pre-specified tolerance. Then we can stop. From this procedure, we can see it is very important to use an efficient strategy to find a new trial point for the next iteration based on the current trial point. If we have a maximization problem, then we can convert the maximization problem to a minimization problem by multiplying the object function by -1. Then we can use this general procedure to search for an optimal solution. From this general procedure, we can also see if we search for an optimum in a very wide range of x, then this procedure is often inefficient. This is because this procedure often requires a lot of trial points and function evaluations. To avoid excessive search within a wide range, and improve the efficiency, a bracketing method should be applied. The key idea of the bracketing method is to keep narrowing down the solution region. Let's see how it works. In this bracketing method, we first assume an initial bracket which should contain the optimal of a function. We also assume the function in this initial bracket is unimodal. If you make a mistake and provide a small bracket, then you will find that the optimal occurs at one of the bounds. So the bracket must be revised until a sufficiently wide bracket is provided. In other words, it will take some effort to find a sufficiently wide initial bracket. In chemical process design problems, we often have physical limits on temperature, pressure, concentration, and other physically meaningful variables. These limits might be used as an initial bracket. After an initial bracket is provided, the general procedure for function value-based methods can be used to scan the variable space in this interval and evaluate the function values at a grid of trial points. Based on the function values of those trial points, we can determine the reduced bracket. In this reduced bracket, we also use the general procedure to scan the variable space in this reduced interval and identify another acceptable reduced bracket. We continue until an optimum is found. Let's use one example to show you how the bracketing method works. In this example, we want to find the minimum of the function f(x) is equal to x minus 100 squared. As we discussed previously, we first need to set up an initial bracket which will include the minimum. We can set up a sufficiently wide bracket like 0 positive infinity or like 0 10,000. If you make a mistake and set up a bracket of 0, 10, then you will find that the minimum occurs at one of the bounds, 0 or 10. In this situation, the bracket must be revised. For instance, if the minimum occurs at 10, then we may find a better solution when x is greater than 10. This is why we need to revise the bracket. After we provide a sufficiently wide bracket, next we need to come up with some strategy to scan the variable space and generate a sequence of trial points that can be used to evaluate the function values. Based on the function values, we can determine an acceptable range for search for the minimum of the function f(x). We can discretize the variable x by a grade of 0.01. That means the trial point at next iteration is equal to the current trial point plus 0.01. Then we can start search at x is equal to 0 and use this formula to find the trial point for the next iteration. If we use this formula, then we need much time and effort to find a reduced bracket. This is because the difference of the trial point for the next iteration with the current trial point is 0.01 is very small. We will generate a lot of trial points to evaluate the function values. Another technique may use a functional transformation. For instance, we can use logarithmic function. So then we can use this function to find the point for the next iteration. That means the point at the next iteration will be equal to the logarithmic of the point at current iteration. Using this formula, we can also look at wide ranges of the variable x. You can also come up with other formulas to find the point for the next iteration based on the point at the current iteration. Of course, the efficiency largely depends on the strategy or the formula we provide. Let's consider this formula that is used to find the point for the next iteration based on the point at the current iteration. In this formula, we have a parameter delta. This parameter is used to control how far we can go from the current trial point to the trial point for the next iteration. Using a bit large value of this parameter, then we can scan successively wider spaced values of x. Let's assume delta is equal to 1 and the initial bracket is from 0 to positive infinity. Of course, you can also assume other values for this parameter delta. We start from 0. This is an initial point we start. This initial point is provided by us. Of course, you can start from other values. At this point, x is equal to 0, we evaluate the function value, which is 10,000. Then we use this formula to get the trial point for the next iteration, that is equal to 1. At x is equal to 1, we evaluate the function value, which is 9,801. Then we can compare the function value at x is equal to 0 and at x is equal to 1. Then you can see we get a better function value. The function value is decreased. So we need to continue. We continue to get the third trial point, which is equal to 3. At x is equal to 3, we also evaluate the function value, which is 9,409. The function value still decreases compared to the function value at x is equal to 1. So we need to continue. The values of other trial points x and the function values are presented in this table. From this table, we can see when x is from 0 to 127, the function value keeps decreasing. We can also see when x is equal to 255, the function value is 2,325. This value is larger than the function value when x is equal to 127, as the function value at x is equal to 255 increases. That means we have bounded the minimum of the function f(x). The minimum of the function f(x) will be within the bracket from 63 to 255. Based on this, then we can identify a reduced new bracket, that is, x is greater than 63 is less than 255. Can we identify the new bracket as 127 to 255? We cannot. This is because we don't have any trial point between this bracket. We don't know if the function value at any point in this bracket is less than the function value at 127. If the function value at any point between 127 and 255 is greater than the function value at 127, that means there is no minimum between 127 and 255. However, we are clear that at the bracket 63 and 255, there is a point whose function value is less than the function value at the bracket bounds. That means there is a minimum between 63 and 255. This is why we have a new reduced bracket as 63 and 255. We reduce the bracket from 0 positive infinity to 63, 255. In this new bracket, we can use the same general procedure and identify another reduced bracket. We keep doing the same procedure until we find the minimum of the function f(x). You can do this exercise by yourself and find the minimum. It should be noted that when the bracket bound decreases, you may need to reduce the value of delta. From this example, we can see the bracketing method is not efficient. This is because we need to evaluate so many trial points and keep narrowing down the bracket. Now, the question is that, is there any other method that is more efficient than this bracketing method?